Logarithms and exponentials, like any functions, can have derivatives. And in this video, we'll introduce derivative laws for these functions, proof of these laws, and how they can be used to solve various problems. To start, let's revise some vocabulary. A derivative is simply a slope of a point of a function. More specifically, it is the tangent line of a function versus the secant line, where the secant line represents the average rate of change, while the tangent line measures the instantaneous rate of change. In order to calculate slope, the following definitions can be used, the first being the direct definition and the second being the alternate definition. As for the notation of a derivative, there is y prime, and then there is Leibniz notation, where the top indicates the function being differentiated, while the bottom part indicates the input of that function being differentiated. So in this case, it is read as derivative of y with respect to x. So let's start with the derivative of e to the x, which by definition is equal to itself times the derivative of its input. Now since the input is x and the derivative of x is 1, it's just equal to e to the x. To prove this, let's start by using the direct definition. So we're going to start by plugging in the function the derivative is being found for. So in this case, f of x is equal to e to the x. Since we're dealing with exponentials, e to the x plus h is the same as e to the x times e to the h by the product rule, where you can basically add the exponents if the bases are the same. Now by doing this, I can now factor out e to the x and pull it out as a constant being multiplied by the limit. Now all that's left to do is to plug in h equals to 0, and when that is done, you'll notice that the answer is indeterminate. Now that doesn't mean that the limit doesn't exist, but that we'll just have to do more algebraic manipulation in order to find it out. So what I'm going to do is plug in small values from either side of the limit, and if they're equal to each other, that means that the limit exists, and so does the derivative. So for the right side, I'll plug in 0.001 for h, and when I calculate that, I get approximately 1. Now for the left side, I'll plug in negative 0.0001 for h, and I too get 1. Now what does this mean? Well, let's go back to what we originally were doing, and instead of plugging in h is equal to 0 for the limit, since we know that this is equal to 1, we can just substitute that instead, and we get the same result as in our definition. Now for a more visual representation of this law, we can simply draw the derivative of the original graph of e to the x. And in order to do this, I'll start by drawing a bunch of tangents at random points, and then I'll plot these values of the slope as y values for the same x values, and that's how you draw the derivative of a normal graph. So we'll start with the first one. I approximate that to be a half. So then I'm going to just plot that right there, half at the same x value. The next is a 1. Again, I'm going to plot 1 right there for the same x value. Then 2, and then 3. And if I connect these dots, and I know I'm connecting them horribly, but I get about the same graph, therefore also proving that the derivative of e to the x is equal to itself. So let's end this by doing a couple of examples. Let's start with this one. And always remember, it's itself times the derivative of its input. So if we were to take the derivative of this, we would times it by itself times the derivative of its input, in which would bring down the 2, times it by x, and plus 3. Now for this example, same idea as before, only this time we'll have to do the product rule. So we'll start by keeping the first value the same, doing the derivative of the second. Then we're going to add the derivative of the first, so this one would be e to the 3x, so we keep the first the same, times the derivative of the input, which is 3, and then times the second one. Using what we know about the derivative of e to the x, let's try to prove the derivative of any exponential base, which by definition is itself times ln of its base times the derivative of its input, which here, since the input is x, its derivative in the definition is 1. So let's prove this by having y equal to a to the x and exponentiating the input by e with ln times a to the x in the exponent, which is actually equivalent to a to the x because e and ln undo each other. Using log laws, I'm going to bring down the exponent so I have x times ln of a. Now I'm going to take the derivative of any function with base e, which is simply itself times the derivative of its input. Now the input here you have to remember is x, and its derivative is simply 1, where ln of a is just a constant. Now since e to the x times ln of a is equal to a to the x, if we replace it with that, we get the proof of our definition. Now let's do a quick example just to check your understanding. So here we again have an exponential function, and we're going to try to take the derivative of this. And remember, it's itself times the ln of its base times the derivative of its input. So what we're going to do, we're going to times it by itself times the ln of its base, which is 3, and finally times the derivative of its input, which is 30x to the power of 5 plus 6x. Now I want to go over one more thing. Many of you have probably noticed that e to the x is also an exponential function. So therefore, the derivative law for any exponential base should also work for e to the x. And that's true. Let's demonstrate this. So remember, the law is itself times the ln of its base times the derivative of its inside. So when we do that, we get e to the x times ln of e times 1. And what is ln of e? Well, that's equal to 1. So yes, this definition can also be used for base to the e, except since ln of e is always equal to 1, it usually isn't written. Alright, so all we have left to do is prove the natural log ln and of any log function. So let's start with ln of x, which by definition is equal to 1 over input times the derivative of the input, which again, since the input in the definition is x, the derivative in the definition is 1. In order to prove this, let's have y equal to ln of x, exponentiate both sides by e, and since e to the ln undo each other, you can cross that out. So that side just equals to x. Now take the implicit derivative of the function, which for e to the y is itself times the derivative of its input, dy by dx, equal to the derivative of x, which is just 1. Now divide e to the y into 1, and replace y with the original input, which is equal to ln of x. Simplify, and we get the same result as the definition. As for the log of any base and input, its derivative is equal to 1 over the input times 1 over ln of the base times derivative of the input. To prove this, let's have y equal to log base of a with the input x, and exponentiate both sides by a. And since any base to the power of log of its base undo each other, we can cross that out. Now take the implicit derivative of the function. So for a to the y, the derivative is itself times ln of its base, so ln of a, times the derivative of its input, which is equal to the derivative of x, so just 1. Now we bring a to the y times ln of a to the other side by dividing it into 1. Replace the input of a with its original value, so log base a of input x. Simplify by crossing out a to the log base of a as they undo each other, and once again we get the same result as our definition. Okay, to check your guys' understanding, we're just going to do a few examples. So for the first one, we have log base of 5 with the following input. And remember, for any of these type of questions, it's always 1 over the input times 1 over ln of the base times the derivative of the input in the numerator. So for this one, we have 1 over the input times 1 over ln of 5 times the derivative of the input, which is 4x to the power of 3 plus 7, and we can just simplify it like that. For the second one, we have ln of input ln of x. So I know this looks a little complicated, but trust me, it's easy. Just remember, for any ln questions, it's always 1 over the input times the derivative of the input. So the input here would be 1 over ln of x, and the derivative of the input is just 1 over x. And simplified, it looks like that. One unique aspect about log laws for derivatives is that they can not only be used to solve those type of questions, but also as shortcuts for finding the derivatives of other types of functions. So let's take this example for instance. If I were to go the normal or expected root way, I would first apply the chain rule. That would be done by bringing down the 3, subtracting 1, keeping the input the same, then timesing it by the derivative of the input, in which we would have to use the quotient rule, as you can see. Then I would expand brackets, because brackets within brackets are improper, simplify, and that would be my final answer. Now, another less confusing way to do this would be using log laws. So I'm going to take the same example, except this time I'm going to do ln of both sides. Then I'm going to use the log law of bringing down the exponent. After that, I'm going to use the log law of quotients, so it becomes subtract, and I'm going to also distribute the 3. Now I'm going to take the derivative. So the derivative of ln of y is 1 over y times the derivative of the input, which is dy over dx. Then for ln of x squared minus 1, 1 over the input times 2x. And for ln of x squared plus 1, it's 1 over x squared plus 1 times 2x. After, I'm going to just simplify, clean up the equation a bit. And finally, times the whole equation by y, in which I would replace y by its original input. Now, you'll notice that the previous answer looks nothing like the answer now. However, I can assure you that they are equivalent. And for some of you, maybe the other way of doing this was easier to understand and perhaps simplify if you need to. However, now you know there are multiple ways to solve one type of equation. Here, for instance, in which I use log derivatives to help me out. Another thing I wanted to discuss is the fact that the derivative of ln of x is actually equal to the derivative of ln of the absolute value of its input. And in order to understand this, let's look at the original graphs and the derivative of the graphs. So for ln of x, in order to draw the derivative, I'm once again going to estimate slope values and then plot them as y values for the same x values. So here I can see that the slope is gradually decreasing and approaching 0 but never really reaching it. So for this first value, I approximate that to be 1.5. For the second, that's a slope of about 0.5, so I'm going to plot that there. For the final one, maybe 0.25, and now I'm going to draw a line to connect all of them. Now for the second one, the absolute value of the input of ln, for the first half, or should I say the left side of the graph, you can see the slope gradually increasing in the negative direction. So I'll estimate the first path as about negative 1.5, and then maybe negative 1, a negative 1.5, etc. I'm going to connect all those dots. Horribly, but I connected them. And for the next part, it seems to gradually approach 0 but never really reach it. So I'll start by plotting that as, I'd say 4.5, and then bring that down to 2.5, and then finally approximately 1, and then maybe 0.5. Connect the dots for that. And you'll notice for both of them, they resemble graphs of 1 over x, which is, by definition, the derivative of ln of x. The only difference is, for the first graph, its domain is greater than 0, and for the second graph, its domain is x elemental real, except x cannot equal to 0. Therefore, whenever you see a question with ln of absolute value of the input, no matter how complicated it might be, all you have to remember is that it's the same value as the derivative of the normal input. Only if you're asked to state the domain would it be different. Finally, let's just summarize the type of derivatives and how to solve them. So let's start with y equals to x squared. And for this one, simply we'll bring down the 2, subtract 1 from the exponent, and we get y prime equals to 2x. Now we have y equals to 2 to the power of x, where now 2 is in the base and x is in the exponent. And in order to solve this, we would apply what we just learned. So itself times ln of its base, which in this case is 2, times the derivative of its input, which is just 1. Now for the final one, we have y equals x to the power of x, where we have both x in the base and the exponent. as well. And as you can see, we can't use any of the previous strategies we did before to solve for the derivatives. So how would we solve for this one? Well, remember how I mentioned logs can be used as a shortcut? We can also apply that here. So if we were to take ln of both sides, then bring down the x in the exponent as par with log laws, then take the derivative of the whole function. So we would have the derivative of ln over y, which is 1 over y times the derivative of the input, which would be dy over dx. The other side, we would have to apply the product rule, in which we would do the derivative of the first, which is just 1, keep the second the same, plus the derivative of the second, which is 1 over x, and keep the first the same. Simplify if you need to, bring y over to the other side by multiplying it, and replace y with its original input, and there you go, you've solved it.